Welcome back to the channel. If you're new here, my name's Jagat, or Jugs for short, and I build stuff on here. Right now I'm into computational physics and mechatronics, so expect to see progress in stuff that I make as I get better and more ambitious in these realms on this channel. So in the last video I introduced this simulation that I made, which is aimed to help physics students visualize different gravitational concepts. So there I covered the physics of these different concepts more in depth, calculations, derivations, and such, just in case you wanted to know exactly what I wanted to cover in this simulation in terms of what these quantities actually mean. But in this video, I'm going to go more into my thought process in building the simulation and how I went about coding it. And I also realized in the last video, which was also my first video on this channel, that it was a little too much explaining without combining it with how it's actually relevant to the implementation and design of the build. So I'll do better moving forward to try to combine everything more cohesively. But yeah, without further ado, let's get into it. Just to recap if you didn't watch the last video. There are four gravitational quantities: gravitational force, gravitational field strength, gravitational potential energy, and gravitational potential. Obviously there are others, but these are the four that were all kind of related to each other that I'm going to model in this simulation. So each of these four concepts describe how masses are affected in the force they feel and their potential energy at different positions in another mass's gravitational field. And they all have different equations, which in this simulation I'm trying to model. If you want to understand these concepts more in depth, feel free to check out my last video or use Google or another YouTube video. So starting off this project, I really had to understand the task at hand. What problem exactly am I solving? So my high school physics teacher, Mr. Nurgundagdu, who I made the simulation in consultation with, described to me that students found it particularly hard to visualize exactly what the equations that we found in the last video described physically. And in addition to this, the concept of infinity distance and its relevance to our four gravitational quantities was perplexing to them, and understandably so. It's a pretty hard concept to wrap your head around. So that brings us to the criteria for the simulation. First, the equations were to be visualized. Luckily, we have a thing in math exactly for this purpose known as graphs. So that would be central to the simulation. Infinity distance was going to be a concept that I had to also pay close attention to and make sure it was emphasized somehow. And lastly, I needed to keep it simple. It's an educational tool, so it shouldn't be difficult to understand nor use. Otherwise, it's just counterproductive. So here's the initial layout that I was thinking. Just to preface as well, I was initially just going to make the simulation for the concept of gravitational potential. Later on, I kind of decided it'd be appropriate to include the three others as well. But initially, I was just thinking that I'd have the point mass at a distance of infinity away from the larger stationary mass, big M. And I'd highlight this because obviously infinity is a very abstract concept, but I really couldn't think of anything better than just a physical point on the simulation that the student could understand as infinity distance away. And this would be reinforced by the restriction of the movement of the point mass beyond this point. I also mentioned previously that some sort of graphical representation would be crucial, hence why there's a graph that captures how the gravitational quantities are changing as the point mass moves closer to and further from big M. And to further spell out this link between the point mass and its present distance and the graph representation even more, I thought, why not include a point mass tracker on the x-axis of the graph? Now there's a problem here that I fixed when coding the simulation, that the vertical infinity line big M should be swapped so that moving the point mass in its direction would be aligned with how the point mass tracker would move on the x-axis. So right now, moving right would move the point mass tracker closer to R, but that would be leftwards. So you can kind of see how changing the orientation would be helpful here. So that was the basis. A user controls a point mass, which with two left and right arrow keys, and can vary the distance from big M from a distance of the surface of the planet to a distance of infinity. And while they do this, a graph should be formed that informs the user how the gravitational quantity is changing. For this project, I use Pygame, which is a multimedia library in Python that allows me to translate code into an interactive visual application. And I was introduced to it by a video where I was able to make a simple planet simulation and thought it was neat for my purposes. And a big advantage of Python for this application is that it's object-oriented, which allows two things. So I learned that the typical way of using Pygame is to have the screen updated at a certain frequency, like 60 frames per second. Which means that a main function where everything is kind of kept and stored runs 60 times per second. And so for data to be kept from one run of the main function to the next, objects can help us with that. Otherwise, if state isn't retained, we lose our data between frames, and it's hard for the application to be a continuous experience for the user. So what that means for the code of this project is that it's going to be predominantly divided into classes. So starting off with the mass class. So this is for instantiating an object as our big M, and it includes constructor and a method for us to call drawMass, which basically just draws our big M onto the window as a circle. Now, for our point mass, we want a lot of the similar attributes. So it's going to be a circle, it's going to be drawn at a certain x, y, but we want some additional functionality in that we can move our point mass. So again, the point mass objects will be the actual point mass, which is moving from the surface of the planet to that infinity line, and another point mass object is going to be our point mass tracker, which is going to move along the x-axis of our graph later on. So you'll notice in our move point mass function that there's this variable that's key to the functionality of the method step. So this step is essentially the change in x position for our point masses that happens per frame that either the left or right arrow key is pressed. And it's proportional to the total number of pixels that spans the path that the point mass can move between. So what this means is for the actual point mass, that step is going to be much larger as its total path distance is much longer, whereas for the point mass tracker, it's only moving along the x-axis of the graph, which is going to be smaller in terms of pixels. That's why its step is going to be smaller. So that actually allows us to segue nicely into the graph class, which is a constructor and a drawGraph method where some visual parameters are accessed, which will draw the graph according to if it's positive or not. So a positive graph would be the force equations, and a negative graph would be for the energy equations. And drawGraph has some usage of an arrow function I found on Reddit, and some other functions to build a visual. So at this point, I kind of had the visual bare bones for the simulation done, and it was time to get some of the physics involved. So how did I collect points to be plotted on the graph? So that really lies in the drawGraphPoint function in the graph class, and it depends heavily on a value called rstep. So rstep is what the step in the number of pixels per frame of the point mass corresponds to in terms of the actual physical distance. So you might be asking what the upper bound of the distance is, since you can't really physically represent infinity meters. It's just a mathematical concept. So what I did was I selected the upper bound that allowed for the asymptotic behavior of the graph to be really captured. So you might be confused by what I mean by this. Essentially, it was just that I found that too large a distance and the smooth curvature in the graph was hard to visualize, and too small, the asymptotic behavior towards zero was not stressed enough. So here you kind of have some comparisons on what the selection for Rmax would be and how they affect the aesthetic of the graph versus what I ended up choosing, which kind of has a nice asymptotic behavior represented and the curvature is not too little or too much. So moving to this drawGraphPoint function, I'm not going to spell out every single line of code here. Feel free to pause and check out the source code more closely, or check the link in the description for the GitHub. Essentially what this function does is it calculates the current gravitational quantities value. So depending on the current R, it'll calculate, for example, for gravitational potential, it'll calculate the magnitude gm over r, or for gravitational force, it'll do gmm over r squared, etc. And then there's a limit in force in that gravitational quantities value. So if little r is equal to the radius of that celestial body, that is when the gravitational quantity is going to be at its maximum value, because that's when its denominator is going to be the least. So after this limit is enforced, it converts the current little r value and gravitational quantity value into an xy coordinate that can actually be plotted. So the way it's plotted is it's first added to a points array, and then r is obviously updated for the next frame. But to draw the actual graph's curve, there's a useful function in Pygame called pygame.draw.lines, where you can pass in an array of points. So as that array is being built, the line will get longer and longer, and more points will be shown on the graph. So now that the bulk of the simulation is done, it was time now to add some customization and opportunities for users to orient their own experience around what they want to investigate. So I wanted to add options there was 3 opportunities to add options to select. So obviously there was the current concept being investigated. So whether it was gravitational potential, gravitational field strength, gravitational force, and gravitational potential energy. What is the current value of big M? So I wanted to vary this by allowing the student to vary between different celestial bodies. So for example, could vary between the Earth, the Sun, the Moon, other stars, exoplanets, etc. And finally, just to vary the mass of the point mass, for concepts where this was appropriate, obviously for gravitational potential and gravitational field strength, that point mass has to be strictly 1 kilogram. But this isn't the case for gravitational force and gravitational potential energy, where it could be useful for these students to be able to vary it and see how that affects the quantities being displayed on the graph. So for my purposes, I found that a button manager class would be pretty useful from which its specific use cases could be inherited from it. And this button manager would, for the specific use case, allow us to use buttons to vary between different options. For instance, for the change planet button manager, 2 buttons could allow us to alternate between the current celestial body being investigated. And also, to avoid handling complex inputs for the mass of the point mass, a change M button manager could allow us to multiply or divide little m by a factor of 10. So a pretty annoying thing that I encountered again was picking an ideal Rmax for each celestial body. And because the big M and the radius of the celestial body would change for each one, this affected the appearance of the graph. And I tried to do some half-assed data analysis, but my brain really wasn't working, so I had to manually test and find each planet's Rmax. Definitely an inefficient way. There definitely is some way to determine the ideal Rmax value based on the body's mass and radius. So if any of you guys have a clue, let me know and I'll adjust the code accordingly. All right, so the simulation is built. Let's play around a little bit and kind of investigate the different concepts that the simulation is trying to help you investigate, I guess. So starting off with gravitational force, let's select little m is 100 kg. And as we move towards infinity, you can kind of see that the force drops really quickly and then kind of levels out. As when it reaches infinity, there's going to be 0 newtons of force between the point mass and our large mass, which in this case is Earth. And so trying out gravitational field strength, so we get little m to be 1 kilogram. We can't change that because that's sort of required in the definition of gravitational field strength. So you see this number, 9.81, and kind of what I was talking about in the last video, that the equations mg and mgh can be deceiving if you don't adjust the value of gravitational field strength depending on how far you are from the surface of the Earth. This is why, because as you go away from the Earth's center or from the Earth's surface, it changes. So if you use mg or mgh at these distances where the g value is actually different, then you're going to get some pretty incorrect results. And obviously, again, when you reach infinity, there's going to be a 0 gravitational field strength at that point, at least from the Earth. So for potential energy and gravitational potential, you kind of see for both there, the graph is upside down. And this can kind of be a confusing concept for students. And I know it's in the equation, but again, the idea of negative energy is a little interesting. But basically what this means is just that you kind of see in the description below here. There's a certain amount of energy at each point P that the point mass needs to completely escape the Earth's gravitational field. And when it gains that energy, say for example, when it's at a distance of infinity, that's when it needs no more joules to escape the Earth's gravitational field. So that's kind of how you can think about why it's negative. And you can kind of see the same thing for gravitational potential. So then we get to 0 joules per kilogram. And it's kind of interesting because we can change the planets. So for example, if you want to see the gravitational field strength at Jupiter, we see 25.9 newtons per kg, which is much higher than, or significantly higher than the Earth's gravitational field strength at the surface. The moon, we know to have less gravity. And we can see that here, it's 1.62 newtons per kilogram at the surface. So that's why the acceleration of gravity, which is equivalent to the gravitational field strength, will be less. So that's kind of playing around with the simulation. It's pretty cool. All right, so that brings us to the end of the video. Obviously, I can only show you guys a portion of the source code. So check out the link in the description for the full thing. Also, let me know, though, if it is too little or if it's too much. Just give your feedback in the comments. And please like and subscribe, a comment if you have any feedback or questions. I'll be responding to every single one, so don't be shy. And see you guys in the next one.